Welcome everyone to the Allen School this distinguished lecture series. It's really a pleasure to host Professor Kunle Olukotun from Stanford University as distinguished lecturer. Kunle is one of my favorite computer architects. I've known him since I was a little grad student and a baby computer architect, and read his papers in grad school, and then got to know him better as I become a faculty and now becoming an old fart. Kunle has done many things. And he does work in computer architecture, does work in programming languages. He also had a very distinguished entrepreneur career, anything from micropayments to big computers, for training machine learning models. And also, as part of I'll say one important record of his career is being part of the, inventing chip multiprocess and actually making it real, and doing a startup company that Sun ended up acquiring and became the basis of their chip multiprocessors. So he has a long list of awards. I'm going to spend time on that, but I just wanted to say, Kunle, it's really a pleasure for you to spend time with us. I told you do have credits to come and for us to wine and dine you and in person here in Seattle. So with that, I'll pass you the token, and thanks again for coming.
Thanks very much for having me, Luis, and inviting me to give a talk. I really miss not coming to Seattle to actually give the talk in person, because, of course, Seattle is one of my favorite American cities, and I like to eat almost as much as Luis, so the opportunity to kind of go out and share a really good meal is something that I will definitely take a rain check on. So today I'd like to tell you a bit about some of the work that we've been doing at Stanford and one of my startup companies, about sort of how machine learning and systems form a virtuous cycle. And if you think about how better computer systems can be, especially those tailored for machine learning, can be used to create higher accuracy models. And these models, in turn, can be used to improve computer systems and so on, right? So the interaction between machine learning and computer systems is actually fairly old. So if you go back, machine learning has been around for a long time, and sort of training neural network models using backpropagation has been around since the 80s. However, if you looked at those models that were around in the 80s, they were much worse than conventional algorithms, heuristics that were developed by hand. So what happened was that as you got more data, you could build more complex models. And eventually, we have the situation today where neural network models are much more accurate than conventional algorithms for things like image recognition and natural language processing. And the key capability is enabled, this ability to kind of train these highly accurate models, is enabled by more compute. And so now we're at this point where you've got these highly accurate models which are trained with huge amounts of data with huge amounts of compute. And these algorithms are reaching human level accuracy. So let me start by focusing on sort of building computer systems that have been optimized for machine learning. Right. So what we want to do, of course, is speed up machine learning. Of course, is being used in every facet of science and engineering, and is pervading society in large ways. And so what we want to be able to do, of course, is enable you to build more accurate models, and with training with large data sets, or serve huge numbers of people with existing models. And so we need to be able to speed up the machine learning infrastructure. However, of course, the underlying performance that we've gotten from Moore's law is starting to slow down, right? And so in order to increase performance, we have to worry about energy efficiency. And in order to do that, we want to create more specialized platforms and architectures that can be much more efficient, right? And so the question is, as we come up with these new, more efficient platforms, how do we balance the needs of performance and efficiency with programmability, right? So, as machine learning improves, or as machine learning algorithms change, we want to be able to adapt to these new algorithms. And so we want programmability, but we also like the efficiencies that one gets from a very specialized implementation, such as you would get with an ASIC. And so the solution to this, of course, is a full stack integrated solution that takes advantage of the latest machine learning algorithms, uses sophisticated compilation to take the algorithms and translate them to optimized architectures. And in order to do this optimization to specific architectures, we need some sort of low-level compilers also. So what I'd like to do is talk about some of the infrastructure that we've, or some of the ideas that we've developed around this idea of taking ML algorithms and translating them to run efficiently on new kinds of reconfigurable architectures. So starting with ML algorithms, let's think about the trends that we see. So one of them I've already alluded to, which is the fact that, of course, that models are getting more complex and bigger. And one good example of this, of course, is the transformer-based models that are used in natural language processing, right? So what you see over time is that these models are going from a few billion parameters to up to the latest model that's being developed by OpenAI called GPT-3, which has 175 billion parameters and can construct prose, which is as good as humans can, right? So what we get then is these very accurate models with huge number of parameters. And in order to train these models, we need hundreds and thousands of GPUs. And of course, as you scale up the number of GPUs, the efficiency with which you are using these GPUs goes down, right? And so you even need even greater numbers of GPUs. And so the critical thing going forward is, of course, to be able to scale to large amounts of compute while keeping the efficiencies are required to not to make sure that you can train very large models. Another trend that you see in machine learning is the use of sparsity, right? So what you'd like to be able to do is maintain the performance of your network without increasing the number of parameters. And a good way to do that is to train a sparse model in which not all the connections between the neurons are made. And so one of the challenges today is sort of how can you train a model in a sparse way, right? So typically what's done today is you train it in a dense way and then you sparsify it later. So an interesting question is sort of how to train sparse models. Another example of what's being done in the machine learning is graph neural networks, right? So here you want to represent people, places, things, and so on, so that you can more accurately model the world and build a model which gives you better predictions. And so graph neural networks are an area that also requires sparsity in order to represent the model efficiently. So in both, in all these models, if you look at the way in which they are described by the machine learning application developers, they're described using what essentially looks like a data flow graph of machine learning operators, right? And so here is an example of, Google shrank their natural language translation code from 500,000 lines of C++ to 500 lines of data flow represented in the TensorFlow domain-specific language, right? So if you look at these domain-specific languages that are being used for describing machine learning applications, they are in TensorFlow or PyTorch, and these frameworks enable you as a developer to very quickly develop your machine learning applications using a set of predefined machine learning operations such as convolution, matrix multiply, pooling, and so on. And in some of the earlier research that we did on domain-specific languages at Stanford, we found out that you could take these domain-specific operators such as convolution and pooling and normalization and convert them into a set of hierarchical parallel patterns. And the patterns represent parallel constructs that tell you about locality and parallelism, like map, reduce, group by, and the like. And not only can you take machine learning domain-specific languages and convert them to these hierarchical parallel patterns, but you can take other parts of the data analytics pipeline, such as data processing represented by SQL, and also represent them using these hierarchical parallel patterns. And so what then you have is a set of domain-specific languages, such as TensorFlow or SQL or Spark, that can be translated into a set of hierarchical parallel patterns, and then you can analyze the parallel patterns to extract parallelism and locality, right? And so what you'd like to do then is take this representation of your application and accelerate it, right? Because we want to build larger models, we want to build higher accuracy, or we want to serve our model to more people. And so all of this needs acceleration and higher performance. And so the key thing that you want then is some sort of representation of your accelerator. And what we've come up with is a representation that represents these hierarchical parallel patterns as hierarchical pipeline data flow, right? And this hierarchical pipeline data flow represents these parallel patterns as pipeline data paths. Because it's an accelerator, it is focused on performance, and so it represents explicit memory hierarchies, gives you hierarchical control and parameters to express your computation so that you can express the parameters of your computation, such as parallelism and memory hierarchy size. And it really is a representation that's focused on being able to express parallelism and locality. It's called spatial. Let me give you a quick example of what spatial looks like. So if you look at this representation of dot product, of course, which is ubiquitous in machine learning, what we have here is two vectors that are defined in DRAM. So notice the explicit memory hierarchy. We're saying vector A and vector B are in DRAM, and then we have tiles of those vectors in SRAM, TA and TB, and then we explicitly load a piece of A into TA and a piece of vector B into TB, and we do reduction within the tile and then reductions across the tile. So that's spatial, a very explicit way of representing the computation in dot product. And so the key thing about spatial then is it gives you these parameters that allow you to talk about tiling and parallelism, and it has some mechanism in the compiler for manipulating these parameters to explore the design space. And so spatial representation is this hierarchical data flow of tiled pipelines with an explicit memory hierarchy, and this is closer to what you want in expressing the application requirements in something that could be accelerated, but it's not as, it still needs some underlying hardware to actually perform the acceleration. And so the question is, what should that hardware look like? And so in order to answer that question, let me go back to some of the things that we talked about in terms of machine learning algorithms. So first of all, there's this notion that you could take the data pipeline and you could convert the data pipeline to hierarchical parallel patterns, and these hierarchical parallel patterns could be expressed as hierarchical pipeline data flow. And so this turns out to be a natural machine learning model. The other thing that we noted was the use of sparsity in both graph neural networks and to kind of limit the impact of to create models that are accurate despite not increasing the size of the parameters too much. The fact that, of course, models are getting bigger in order to get a higher accuracy. So state-of-the-art accurate models for natural language processing, as I said, are in the 100 billion range. And lastly, you want some ability in your accelerator to be able to map your computation graphs from your machine learning algorithms in different ways, right? You want to be able to exploit different kinds of parallelism in the graph. You want to be able to exploit model parallelism within the graph, and you want to be able to exploit data parallelism across multiple instances of the graph. And so the ability to support flexible mapping with high efficiency is a key requirement in your accelerator hardware.
Can I ask a quick question here? Is that just a quick perspective question here?
Yeah.
So I was just wondering, what are your thoughts on, well, of course, we had data flow focused languages and execution models, and even the data flow hardware for a long time. And now there's this whole rethinking of all of that for machine learning workloads. What do you think is special, is different in machine learning workloads that wasn't, the case for, workloads that people thought of when, data flow and earlier efforts in that space were a thing, So is there any significant change in the properties of the workload?
The key significance is the core, is the granularity of data flow, right? So all the old data flow ideas that were initially, some of the work that was done at Washington were kind of focused on, sort of data flow within what I would call a basic block, right? And where here we're looking at data flow across the whole program. And I think the granularity is important. I think the fact that these algorithms tend to be less control intensive than the ones that we were looking at earlier allow you to do optimizations that we didn't focus on in the earlier instances.
Yeah, that makes sense. And I completely agree with that. And I also think that perhaps the computation intensity is different, right? So now we have a lot of data and little computation as opposed to little data and lots of compute. The ratio of computes to data is probably very different in machine learning than other workloads before.
That's
right?
true.
So, yeah.
That's also very true. Yeah.
Cool. Great. Yeah. Thank you.
Yeah. And so what you get then is an architecture optimized for executing these hierarchical parallel patterns, right? So you've got spatial that give you these hierarchical parallel patterns. Then what you want then is an architecture that is optimized for that. And the architecture that we came up with is called Plasticine. And it has both configurable compute units that we call pattern compute units and configurable memory units that we call pattern memory units. And these have the ability to be a very good target for mapping spatial programs. And the result is that you can get a tremendous performance and efficiency and programmability benefit over a fine-grained reconfigurable architecture like an FPGA. And one way to think about Plasticine is it's a very, very coarse reconfigurable architecture in that, we're thinking about these units as sort of tens of ALUs that are being reconfigured as opposed to, what are traditionally thought of as coarse-grained reconfigurable architectures, where we're reconfiguring things at the individual ALU level. So let me delve into a little more detail on sort of what Plasticine looks like. So the pattern compute unit you can think of as a component which is focused on exploiting nesting parallelism. So you can exploit parallelism in a pipeline fashion because you've got pipeline stages within the PCU. You can also exploit parallelism across the pipeline stages in a vector manner. And you have support for data locality provided by the programmable memory units, called the PMUs. And these have their own address generation units, so you can do decoupled access execute, which of course is a very powerful mechanism. And then you also have the capability to reconfigure the memory to support the data access required by the computation, right? So for instance, if you want to exploit parallelism, you might want multiple banks that can be accessed independently. If you want to exploit pipeline parallelism, then you want multiple buffers that can be supported. And so you want to be able to reconfigure your PMU to match the computation that's being done. So to give you an example, so kind of the full advantage of spatial and reconfigurable data flow architectures as a compelling alternative to CPUs or traditional data flow is really the ability to exploit this spatial parallelism by unrolling the computation across the chip to extract massive amounts of vector, pipeline, and stream level parallelism. So you want all of the above so that you can get very good performance. So to give you an example, here's a spatial mapping of some nested for loops, which could be parallel patterns, but for loops are probably more familiar to you. So in here, we've got a control hierarchy where we've got an outer for loop A and two inner for loops B and C, which are all accessing a common memory. And so what we want to be able to do is spatially unroll the computation so that you can exploit fine-grained parallelism within the basic block, and then coarse-grained parallelism across the control primitives, including loops and other control flow operations, right? So within any of the loop bodies, you've got some set of operations that form a data flow graph. And to Luis's question, traditional data flow kind of focuses more on thinking about what happens within the basic block. And where we really get power is the ability to do data flow across the basic blocks. And one important method of doing this is what we call hierarchical pipelining, right? Or meta pipelining. So this is the ability to pipeline across multiple loops. So in this case, what we're doing, we've got operations in loop B and loop C, which are being pipelined across the machine, creating a pipeline that goes from loop B to loop C. And of course, the depth of that pipeline is the number of operations in the body of loop B plus the number of operations in the body of loop C, so X plus Y. And this, as we know, the throughput increase is going to be the depth of your pipeline, and so you get both of these together, right? So that's one degree of parallelism, the ability to pipeline, and you can do this at multiple levels. And of course, in order to make this work, we know that pipelining requires that you have some extra buffering so that you don't mix up your pipeline stages. And so you need to be able to add the buffering, and the programmable memory units, the PMUs, provide this capability. You also want to exploit vectorization within the inner loops, right? So you want to be able to vectorize. So that's just typical vectorization. And you also want to be able to parallelize across the outer loop, right? And then you want to be able to stream between the outer loop, right? So you put all this parallelism together, and you have a huge amount of parallelism that you can extract from these applications. And you want to be able to extract this parallelism such that you can use up all the compute capability of the machine. And so, when you're all done, right, from this loop nest, you get X plus Y times M times N numbers of ops per cycle, which is far higher than the old data flow architectures used to get. So, the one question is, given a representation like spatial, how do you map it to a data flow architecture like Plasticine, right? So you've got to do two things. You've got to take the computation expressed imperatively and map it to data flow. You've got to figure out how to handle control flow operations that are not loops. You need to figure out how to make sure that even though you've got this distributed computation that are accessing memories all over the place, that you keep correct memory consistency, and you maintain the memory consistency that the programmer thought. So the component in the compiler stack that does that is in Plasticine is called SARA, and it does two things. It both does this mapping of imperative spatial to the data flow representation, and then it also partitions the data flow representation to match the constraints of the underlying architectures, such as how many pipe stages do you have, how much memory do you have, such that you can actually get a representation that works. And then there's some other optimization that goes on to improve performance. And so once you have run the spatial intermediate representation through the SARA compiler, what you get out is a representation that can actually be used to configure an architecture like Plasticine. Now, let's get, all right, so what you get, so the nice thing that you get is you get this unrolled computation that for your whole application, hopefully, or as much of your application as you can fit on a chip or across multiple chips. And the nice thing that happens is that the communication stays local, right? And so if you think about the way that GPUs do computation, they take one kernel at a time and they execute it to completion, and they dump the results in the high bandwidth memory off chip. And then the next kernel comes along and pulls the results from the high bandwidth memory and generates its results and puts its results back to the HBM. That creates a lot of extra memory traffic that is eliminated with this kind of spatial layout of the computation. And the result is much less memory bandwidth and much higher performance and much higher efficiency. So you get a lot of benefits. And the big benefit of a much lower memory bandwidth is in a lot of situations, you don't need high bandwidth memory. And if you don't need high bandwidth memory, then you can get away with DRAM. And if you can get away with DRAM, you can get much, much larger memories. And so the result is that now you can think about doing these problems efficiently without high bandwidth memory. And now you can build, you can do much, much bigger problems. And so that's a big benefit. And so we did this initial work. We published a paper in ISCA in 2017, and we were so excited about results that we quickly decided to start a company based on these ideas. And the company's called SambaNova, and Luis has got to like the name because my co-founder is a Brazilian, and so and
he likes samba too, I assume. Huh?
Yeah, exactly. And the other co-founder is Chris Ray. Of course, Chris Ray got his PhD from University of Washington, so you guys know him there. And so the first chip that we have designed is called the Cardinal SN10, and it's a reconfigurable data flow unit. This is what we're calling it. It was the first machine learning accelerator to be implemented in TSMC 7 nanometer. It's a huge chip, 40 billion transistors, over 50 kilometers of wire, the ability to do hundreds of teraflops of computation for machine learning applications, 100 of megabit bytes of memory on chip, and direct interfaces to terabytes of memory on chip.
Cool. Yeah. On that note, so a quick question on how do you provision? How do you think about provisioning? Some of the specialized function blocks. I mean, of course, being reconfigurable is great. You don't have to make some decisions about workloads, until you actually use it. But you still have to make decisions about how to provision hardware resources such that you at least aim at a target classes of workloads that you're going to do especially well. So how are you thinking about it here?
So, the first target is clearly, the broad range of machine learning algorithms, right? So it's going to be, is that
Yeah, so just thinking about like if you have for the more fixed function blocks that you have in your reconfigurable fabric, so there's some decisions that you probably need to make there that's you're probably gonna have less reconfigurability. Like, if you're gonna have any sort of like hardwired, operators, convolutions, or capacity to bandwidth ratio.
So there's nothing really hardwired in the architecture, right? I mean, it's basically all you've got. The only thing that's hardwired is the fundamental functional units, right?
Right. I guess that's what I was asking. Like, how are we thinking about the distribution of types of functional units that you're going to bake in?
Yeah. So there's some capability that you have, right? So sort of how you do the addressing of your memory, how many banks you have in your scratch pads, what kinds of operations do you have in the different pipe stages. But these are all kind of fundamental decisions that you would have to make in any computer architecture. And so our whole goal is sort of how can you get efficiency without kind of tying the hands of the algorithm designer, right? So you want freedom in what sorts of algorithms you can execute, but you still want efficiency. And the way you get efficiency, of course, is by not paying the overheads of instruction fetch and decode, and being able to exploit parallelism at all levels as efficiently as possible.
Yeah, thank you. Just one more thing. So Joseph McMahon, you want to ask a question since you raised your hand now?
Yeah, I just had a question about this chip. Despite its behemoth size here, these networks we're looking at now are so large, I assume you can't fit a whole network on chip, right?
Yeah, it depends on the size of the chip. It's the size of the network. Yeah, right. But yeah.
Sure. But yet, on a previous slide, it mentioned that the switches in Plasticine are statically programmed, right? So how do you change that spatial architecture as you load on different parts of the network at different times?
Well, they may be static for the particular network, but you can change them.
Yeah, but I'm within one network. If I do the first half of BERT and the second half of BERT, I assume I need to relay out what I'm doing.
Yeah, so you just reset the configuration of the
okay,
chip.
So there's a reconfigure operation.
Yeah,
okay,
absolutely.
Okay. I understand. Thank
you. And it's fast enough to actually do this context switch for a given model.
Yeah.
Great.
And you can imagine that you could do part of the,
Right.
Yeah, right. So it could be partially reconfigurable.
We have one more question, if you don't mind.
Yeah.
Professor Michael Bedford Taylor.
Yeah.
Hey,
you know that guy?
Hey,
yeah. Hey, Mike. How's it going?
Good to see you. Good to have you here for the talk. Yeah, so I had a question, just getting back to Louise, a kind of more concrete data point. So, in terms of hardwiring things, you presumably you have to handle floating point computation, and anything that's parallel has to have a lot of little small memories to give you memory parallelism. So, in terms of like just a basic ratio of like how many floating point units per 4 kilobyte memory, like what's the ratio look like?
I'm not sure I remember the answer, and even if I did, it's not clear I could tell you what it is. But I don't.
But like kind of rough, like just as a not specific to the architecture, but in your opinion, like ML chips that are doing training, like what is that ratio? What should it look like?
What should it look like? Good question. I don't know off the top of my head. Okay, so what you'd like to do, of course, is combine multiples of these chips together so that you can train very large models. Hence the question from Joseph, right? And so you could, of course, given the amount of memory, we can time multiplex the resources. But if you want to be as fast as possible, you'd like to spatially lay out your network across multiple chips. And so you want to be able to have systems composed of these chips. And SambaNova's got 3 different size systems: a quarter rack, a half rack, and a full rack. And the amount of memory associated with those racks goes from 12 to 48 terabytes. So what sorts of things can you do with this architecture, right? So our focus is on creating some systems that enable new capabilities. We call these 0 to 1 transitions, focusing on the sorts of problems that are important in the machine learning arena, such as large 100 billion parameter natural language processing models, which have become the key to knowledge understanding, like GPT-2 and GPT-3. the ability to do very high resolution image model development. So 50,000 by 50,000. If you look at a lot of the problems in astronomy, medical imaging, oil and gas, they turn out to be large machine learning models with high resolution. And then recommendation, which of course are very important in internet services, right? You know, over 70% of the computation that runs in the machine learning component of Facebook is in fact recommender models. So in the area of large natural language processing models, using SambaNova systems, you can build 100 billion parameter models on a quarter rack, right, with 8 RDUs. Compare this to NVIDIA, and for NVIDIA would require 54 A100 GPUs or 8 racks. In the arena of high resolution image deep learning, we can train 2K by 2K astronomy models to much higher accuracy than NVIDIA A100 because NVIDIA A100 cannot train very high resolution models because they run out of memory. In the arena of recommenders, we can get very large embedding tables which allow you to get state-of-the-art accuracy on deep learning recommendation models, DLRM, and you can get 5 times faster training and inference compared to an NVIDIA A100. So the point here is that these kinds of reconfigurable data flow architectures can make meaningful impact on very large models that people want to train in the machine learning arena.
So, Kunle, to put this in perspective, there was a question here that was sent to me, so I'm going to try and complement it a bit. So, can you give us some comparison points here, making something the same? Like when you compare against NVIDIA, how much more hardware resources do you have? Or if you were to compare on other metrics, like throughput per dollar, or throughput per watt, how can you give us a sense of where?
So here you've got in the case of your natural language parameter, natural language processing, you're using 100x less power, right?
Okay.
In the case of this high resolution deep learning, it's a case that you simply can't do this problem with a NVIDIA GPU because you can't handle the high resolution. So the comparison isn't even possible.
Isn't possible. I see.
Yeah,
cool. And the hardware resources are roughly the same, or if you to put a number of, just put a metric like an amount of silicon between the two of them,
Yeah, roughly. I mean, you look at A100, and they're roughly the same sort of order of magnitude in millimeters squared of silicon. Yeah,
I see. And also, Hank also had a quick question. Hank, you wanna ask a question?
Yeah, I was just asking the same question, but about sort of Google's TPUs and latest TPU system. Same question, basically.
Yeah. So I think that if you look at the TPU, they've gone all in on matrix multiply, of course, as you know.
Right.
But matrix multiply isn't everything that you do in machine learning, and it's dense matrix multiply, right? So it doesn't handle sparsity that well. And so with our architecture, we can go from dense to sparse fairly easily because it's reconfigurable and it has the capability to do sparse matrix computation very efficiently. And so in comparison, you look at the Google approach, and there's the things that they do outside the chip, right, or the chip-to-chip interconnectivity that they have, which is fairly impressive that we don't currently have. But in terms of the chip itself, we think our chip is much more flexible.
Thanks.
There's a bunch more questions. We're going to hold them until you make more progress on the talk, Kunle.
Okay.
So.
And then lastly, if you're saying that the chips are roughly the same in terms of resources and power, then 5x faster training and inference is a 5x improvement. All right, so so that basically is sort of where we are today in terms of support for machine learning with a reconfigurable data flow architecture, and how it matches the kind of requirements of the application space, and how you map the domain-specific operations that are exhibited in machine learning applications down to the reconfigurable data flow that you need to drive the configuration of an architecture like Plasticine. And so the question becomes, okay, so you decide to deploy an accelerator in your data center, and you'd like to accelerate more than just your machine learning. You might also want to accelerate your data processing, your SQL, and you might want to do it with the same accelerator, right? You want what people have called general purpose, special purpose, or special purpose, general purpose, right? And so you'd like to not have to deploy 2 different accelerators or 3 different accelerators, or an accelerator for every different problem domain that you might think of. And so the question is, what would you need to do to a Plasticine style architecture to have it support more types of computation, in particular relational database sorts of operation? And so that was the point of Gorgon, right? So Gorgon, accelerating machine learning relational data. And so the idea is that you'd like to be able to run queries that combine machine learning and data processing, right? So in some sort of unified reconfigurable data and analytics accelerator. So you could have a query where you have a aggregate table and a join of 2 tables, and then you train on the result of this join, right, as described in this query here. And so in order to run a query like this, you need to augment the sorts of parallel patterns that we currently execute efficiently in Plasticine with parallel patterns such as described here that can do partitioning of tables, can do sorting of tables, can do group by of tables, can do joins of tables. And so it turns out that in order to provide this sort of capability, you don't need to add too much more support to the capabilities that Plasticine already has, right? So there's some extra logic that you need to add to the pattern compute units. And the total increase in chip area for this is roughly 4%. And you have to kind of construct your database records in a way that allows them to be vectorized. And so there are a bunch of different queries that we came up with. There were no benchmarks that kind of really represented the kinds of operations that had this combination of machine learning and database queries tightly coupled, and so we had to come up with ones ourselves. And the comparison between a Apache MATLAB running on a conventional Intel CPU and our accelerator Gorgon, you see tremendous improvements compared to doing things purely in software. So the point here is that you can take a architecture like Plasticine and augment it with some extra capability and be able to attack an application area like database. We've recently shown that you can actually even do graphs very efficiently, and you can do pointer-based data structures like tree, B trees, and trees very effectively. And the key idea really is to transform threads and control flow into data flow. And so what we've shown is that you can take these models of computation that traditionally people have thought of as very sequential and very irregular, very data dependent, and you can make it so that it runs very effectively on a vectorized architecture like Plasticine. And the key mechanism that you need is really this extra support that we've added in Gorgon, this ability to do operations such as sorting, filtering, and group by on records.
And I presume this is because you also want to be able to mix database capabilities with machine learning inference like in the same workload. Because if you were to just do database, you probably would look at a slightly different architecture too, right? So,
right.
So is that the idea, or is it just such that you can sell your chips to different classes of customers, or is it really because you're doing both of them because you want to see both of them being done together in the same workload in the same chip?
Well, because people want to see, they want to do. Potentially, they want to have database operations in the core of their machine learning training loop, right? And that might be beneficial to the sorts of things they want to do. And also because even if you didn't have it in the core of your training loop, the first thing you'd want to do in order to create your training data set would be some sort of SQL kinds of data processing operations. And so why not put that on the same accelerator? And now you don't have to move the data, and now you only have to buy one accelerator instead of two.
Right. Yeah. But the only reason why not is that then you're taking some silicon away from other things that will be. It's again, it goes back to the question: how do you provision a set of? If you have a certain silicon budget for functional units, like how do?
I think whenever you think about these mechanisms, you want to think about general mechanisms that are not just good for database, but are also. There's this notion that sparse computation databases joins are basically the same thing, right? So if you think you can do databases efficiently, that means you can do sparsity efficiently, which means that you can do the future of machine learning efficiently.
Right. But you compromise some efficiency. I mean, I'm not crazy. I'm just thinking about it's one more trade-off that you have to think about ahead of time too, right? So you do compromise efficiency in some use cases, but
yeah. But what we've shown is that you can do as well as the database, the pure database accelerators.
Right. Cool.
So you might be giving up something, but not that much.
Right. Yeah. So Michael had a quick question here, and then we should let you make more progress. Mike, is it quick? You want to ask the question?
Yeah, sure. It gets back to a little bit. You were showing some great results about the memory capacity of the system you guys had built, and I was wondering if you're seeing in the ML server silicon domain, do you see some kind of segmentation that's going to happen? Are machine designs going to start specializing within ML?
That's a good question. So there was the notion. Well, until recently, that there would be a specialization between training accelerators and inference accelerators, right? So the notion that the training accelerators would be optimized for large batch operations such as GPUs and TPUs, and then inference accelerators would be optimized for kind of batch one operation. We think that the two are converging for all sorts of reasons. One is that there are some models that you want to actively, do online, real-time training, right? So you want to constantly update the model as you're serving it, right? And so you'd like to be able to do efficient training with large batches at the same time you're doing, single batch inference. But beyond that, I haven't seen, one could imagine that you could have something that was just good at doing convolutions and wasn't that good at doing natural language processing. But, if natural language processing is dominated by transformers, which is basically matrix multiply, that's not too far away from convolution. So I haven't seen any real specialization beyond the notion of training versus inference. Okay, so now let's talk about, let me end by talking about the other part of the virtuous circle, the idea that sort of machine learning can be used to improve systems. So in this example, I'm going to focus on networking, right? And how machine learning can be used to improve networking, right? So you think about networking, and there are a number of different heuristics that get used in different parts of networking. So you have heuristics for improving security, for detecting anomalies, or for classifying traffic. You have heuristics for congestion control and queue management. You have heuristics for analytics. And so the idea is that you could replace these heuristics with machine learned models, and you could get both higher accuracy or better operation than you could with the heuristics, and potentially you could get if you did it right, you could potentially get sort of more predictable behavior. So what's the problem with kind of trying to apply the idea of sort of machine learning in say a network switch, right? So you think about the network architecture, right? You have the control plane, which kind of makes the decisions on maybe a packet flow basis, and then you've got the data plane, which is actually moving the packets. And so you can think about trying to do an intelligent network environment where you have decisions that are being made on a per packet basis, as opposed to sampling what happens at the per packet basis by the control plane and making decisions there. So the problem with kind of doing the decision making at the control plane is it takes too long to get back and forth between the control plane and the data plane. So here are some examples of a DNN for doing anomaly detection on different accelerator platforms that are put in the control plane. And so, you can't afford, given the bandwidth restrictions, to send every packet to the control plane, and the latency becomes too high. But yet, if you look at the data plane is, traditional networking data planes are not optimized for machine learning, right? The kinds of computation that they do, the kinds of acceleration that they have in the data plane isn't very optimized for doing machine learning computation, right? So what you currently have is you've got a packet parser, which will look at the packet headers and decide what to do by using these sort of match action tables, right? And so the project that we have going on at Stanford is called Taurus, and it's being done by Mohammed Shabazz, who's a postdoc who recently has become an assistant professor at Purdue, and my PhD student, Tushar Swami, I should say. And so the key idea is to say, take the Plasticine architecture and insert it into the data plane of a network, right? And so the idea is you've got the ability to do efficient machine learning, and now you have a data plane that looks like this with the Plasticine component. We call it Plasticine RT since it's a cut down version of Plasticine. And so what happens then is you pass the packets, you read the headers, and you look at the features, and you retrieve the network events that are going to be used to drive the machine learning model. And then you basically going to select some options. So if you see an anomalous event, for example, you say, drop the packet, right? And so you've got these match action tables on either side of a machine learning optimized accelerator. And so you can't get Plasticine in the middle of a set of match action tables today. And so we approximate this kind of architecture with a Taurus testbed, which has the different components of the networking switch in different systems, right? So you've got a control plane, which is of course a traditional server, and then you've got a Tofino switch as your your match action tables, and the FPGA is basically doing the Plasticine capability, and you have all of these connected by 10 gigabit and 100 gigabit Ethernet links. And so then what can you do with this sort of setup using a Taurus-like data plane? Well, you can do anomaly detection. And so this graph shows what happens when you do anomaly detection, and you compare Taurus with the, shown in blue, with the operation doing the running the inference on the control plane, which is shown in green, right? So the idea is that as you increase, as the event rate increases, because the bandwidth of your network increases, the Taurus, which is doing the inference at the data plane, works at full rate, but the control plane inference can only sample at some rate, and as you increase the bandwidth of your network, it can't keep up, and so you've got this gap between the rate at which the anomalous events occur and the rate at which you can actually send them to the control plane, and the impact, of course, is going to have an impact on the accuracy, right? So if you look at the model is capable of an F1 score of 71. But if you look at what happens in the software implementation, the F score goes from a high of 1.5 to 0.001. So what you're seeing is what happens when you don't get to see every packet. So Taurus gives you the accuracy that you would expect by looking at every packet, which is almost 60%. At the high data rate, but if you look at doing the control plane implementation, now you're down, once you get to significantly high data rates and anomalous event rates, your detection goes down to 0. So the point here is that by applying Taurus-like ideas where you are doing inference at the packet rates, and you're doing it in the data plane, and by using machine learning, you can get much more accurate results. And so here's an example of using machine learning to improve data center networking, which then could be used to build better machine learning environments to train better models, and the virtuous cycle continues. And so what I've described today then is this virtuous cycle. I've described a path going from optimized computer systems to enable you to build higher accuracy models in a wide range of machine learning applications, from natural language processing to recommenders. I've also described kind of using machine learning to improve networking systems. I described the Taurus ideas and using them to drive the ability to look at every packet and make inferences on those. And a future work would be, can you train these models in real time by doing training in the network at in the data plane at full packet rates. And this, of course, could lead to better data center networks, which could then improve your overall system for applications that include machine learning and beyond. So at this point, I'll stop and ask if there are any other questions.
Great, thank you, Kunle. This was awesome. Okay, all right. I know we're a little bit over time, but if Kunle is okay with it, we can take a few more questions.
Plenty of time. I'm on the West Coast like you guys.
All right, cool. All right, so you can either jump in the voice live here or type in the chat here. Any other questions?
Okay, I have a question if there's no.
Yeah, go ahead.
I'd love to just hear more about how control flow is handled as you lay things out spatially on Plasticine. It feels like, I feel like I have a good grasp of how you would do that for a CNN or a static data flow network. When you start getting into data-dependent control flow, it's not clear to me how you can efficiently.
Turns out there's a bunch of, I didn't describe, there's a bunch of token control that goes on. And so the control is actually done with tokens, and that's the way that you do the control flow. So what I did not show you is the control, analogous to the data flow networks. You have control flow networks that keep track of how much data is being generated where, and that's the way that you can actually do control flow.
Okay, thank you.
And so I have a question. I hope it's not going to sound self-serving here, but I'll ask. So by the way, we're having TVM Conf going on these, today and tomorrow. And, one of the things that, open our eyes and working on TVM is that how much diversity there is at the top of the framework level and the model level, that even if you have great hardware, if you're not ready to always take advantage of the latest advances in the machine learning models, you just can't move fast enough, right? So how are you thinking about in the software stack, either with your professor hat or with your SambaNova hat? So how are you thinking about, keeping up with all of the fast changes going on in models and the rest of the machine learning software stack?
That's a really good question. And the key, as you might expect, is to have the ability to have a very quick way of creating these low-level templates, right? So we've got compiler technology that can create these templates, and so you want multiple levels of compiler. You want the ability to very quickly develop optimized templates, and you want the ability to compose these templates in different ways, right? So, and you want to not have to require that you create custom huge templates, right, for every situation. What you want is a small set of templates. And if you kind of look at the low level, things may be changing drastically at the high level, but the low level, it still comes down to a few set, MHA, concat, matrix multiply, convolution. There are not that many templates that you need. And then you want the ability to be able to compose these templates in any way that you can and get very good performance. And that's what we can do, right? So the key is composition. The key is, can you put things together and get the same performance that you would have gotten if you'd written a fused template or fused operator?
Yeah, I think that makes perfect sense. Yeah, and I completely agree with that. And on a slightly different dimension of what's going on at the top level of the software stack for machine learning, I think it's also interesting how the programming models are changing, right? So before you went from a bunch of custom code in various languages, C, Python, whatever, to, going to something like MXNet, TensorFlow, and PyTorch, a largely library-based approach that's now becoming more of a language approach. Now you look at JAX or Torch script, it's becoming, again, a general-purpose language that is becoming, a free-for-all, do whatever you want, which is actually complicating a lot the process of actually translating this down to any specialized architecture. So I think there's something interesting there that maybe AI is going to help us rewrite these programs, but otherwise I don't see any other way to do this efficiently,
I mean, ultimately, right, for us to do, to get very good performance, we need to see as much of the computation graph as possible, right? If you give us a kernel one at a time, we're never going to beat NVIDIA, right? The key is we need to see the whole computation graph and figure out how much parallelization should we do at each stage so that we have a balanced pipeline. At the end of the day, we're hardware designers. We want to build a pipeline. We want to make sure that we keep that pipeline going at full rate. And we want to make sure that all stages are balanced. We want to make sure that we don't use up the memory bandwidth, or, there's all these trade-offs between, how much recompute do you do and how much memory bandwidth do you use, right?
Yeah, that's right.
How much model parallelism do you use versus how much data parallelism do you use?
But this changes as models evolve. I mean, it's not as a single model. Like with dynamic models, the same model evaluation depends. The previous layer can tell you how much parallelism you have in the next layer as you have control flowing models. I think it's super interesting that all the mistakes that we made early on in making programs, really hard to extract ILP from, it's starting to happen again in machine learning models, in my opinion, because you start getting dependence between layers, and now all of the beautiful clean parallelism that you talked about so far, right? So it's starting to go away with these new models, right?
So you need dynamic mechanisms. And what I didn't talk about was the latest stuff, and it's really cool, is the ability to with the same basic architecture, get very dynamic kinds of computation.
Yeah, I believe you, especially when you said that the reconfiguration is so fast that if you can actually react to changes in data, right? So
reconfiguration is fast, but also you can build data flow. You can build data flow computation that is dynamic, right? You say, I'm going to sort these. I'm going to keep my thread context in the data, and I'm going to use sorting operations to say this set of threads goes one way and this set of threads goes the other way.
Yeah, that's right. You have dancing dependence edges all over the data flow graph, right? Well, with that, let's see if there's any other questions from the audience. Otherwise, if you let, Kunle and I are going to be chatting until tomorrow morning. So, Kunle, thank you again. Nice seeing you. Looking great. Thanks again.